This is our second recitation, and today we will talk about electric field. We know that force between two charged particles is K, magnitude of Q1, magnitude of Q2 divided by distance between them squared. And I put unit vector R in radial direction. R is unit vector in radial direction. We introduced electric field. Electric field, I remind you, is limit with test charge Q naught to 0, force between two charges divided by Q naught. Q naught is test charge. It's by definition positive. Q naught to 0 means that if I put Q naught somewhere, it does not disturb the distribution of all other charges, does not change forces between these charges. And we also found electric field created by point charge, which means that I take Coulomb's force, I divide by one of these charges, and electric field created by point charge is coefficient K. How do we call this charge? Let's just call it Q divided by R squared. I divided by Q naught. Then there is just Q over R squared. And then unit vector in radial direction. So today we will use electric field created by point charge to find electric field created by some distribution of charges. And the first problem that we will solve, I will erase this. The first problem that we will solve will be with two charges. Charges Q1. Let's have them have the same magnitude and let them be negative. So I have minus Q1 at distance A from the origin. I have minus Q1 at distance A from the origin to the right, and I have charge, positive charge Q2 at distance B below origin along Y. And what I'm interested in, I'm interested in electric field created at point x0, yh. Find the electric field. The electric field at point x0, yh. Which formula we will use for that? We will use this formula. Electric field is coefficient kq over r squared, unit vector in radial direction. And we will draw an electric field created by all these charges at point y equal to h. So what will be electric field created by positive charge Q2? Electric field created by positive charge Q2. So how to think about it? You put charge Q naught right here. Both are positive. Then the force will be repulsive force, or electric field will be in the direction along y. So this is electric field created by Q2. I put E2 here. So let's write it a little bit closer. E2. Then I will draw the electric field created by charge minus Q1. So what will be electric field created by minus Q1 at this point? If I put test charge Q naught here, the force will be attractive. And we understand that direction of the force exerted on the charged particle is QE. We talked about it during the lecture. And if I have positive charge, then electric field is in the same direction as the force. If I have negative charge, then electric field will be in opposite direction. So force is QE, and I just wrote this formula for arbitrary Q. So this, we call it, how we will call it? Let's use L for the charge on the left. I will use L for left, and I will use R for right, for the charge on the right. Electric field created by this left will be EL, and the electric field created by this right charge will be again towards the charge because it is negative, and I put here ER. Okay, so what will be total net electric field? Electric field at point 0H will be vector sum of electric field EL plus ER as a vector. We add them as vectors, plus E2. What we need to do next, we need to express each of these electric fields in terms of components, and then add all X components together and all Y components together. So let's start with E2. E2. This electric field is in positive Y direction, and magnitude is K, charge Q2, divided by distance, which is B plus H squared, distance squared, I'm right here. It doesn't have X component, but it has, this is Y component. It is along positive Y, I put IY here. We are done with E2. Now let's find E left, but before we do that, let's look at this picture again, and if we do that, I did not draw it accurately, I will improve it a little bit. So if you look at it, we will see that X components of E left and E right have the same magnitude and opposite direction. So from symmetry, E left X plus E right X is 0. Net X component is 0, created by left and right. Y components are non-zero. Let's find Y components. We can find Y component created, let's say, by right, and then just multiply by 2. What will be E right Y? E right Y is this leg of triangle. It is negative. Y component is negative. This is our hypotenuse. Let me bring ER here. This is ER, hypotenuse, and it is, this vector is vector sum of this and this vectors. Y component negative, I put minus, and then it is K, Q1. Do I need to put minus Q1 or Q1? Magnitude. We already took into account minus right here. Y component is negative, and here I put magnitude of Q1. Q1 divided by distance squared. Distance between Q1 and point of interest where we are looking for electric field is this. We will use this triangle to find this distance. This leg is A, and this leg is H. So hypotenuse is A squared plus H squared, and distance squared is just A squared plus H squared. Now we need to write Y y projection, y component of this electric field, let's introduce this angle. This will be theta. Then this is also theta. And y component will be just this hypotenuse ER times that we already wrote, magnitude, and then times sine theta. One from left will be the same, so we have E left y will be also minus k q1 over a squared plus h squared sine theta. What is sine theta in terms of what is given? Sine theta is opposite leg h divided by square root of a squared plus h squared. I will bring sine theta here. It is minus k q1 divided by a squared plus h squared times sine theta, which is h, divided by a squared plus h squared to 3/2. This is y component. This will be exactly the same. I will not rewrite it. I'll just take this one and multiply it by 2 eventually when we add components. So what will be net electric field? It will be total x component of left is 0. Sum of x components of left and right is 0. X component of E2 is 0. No x components of the resultant. What will be net y component? ELY is equal to ERY. We will have twice and then minus k q1h divided by a squared plus h squared to 3/2. And then y component of E2 will be k plus k q2 divided by b plus h squared. And all this is y component because x component is 0. So we found net electric field and point x0, yh created by these three charges.